Hey guys, how's it going? Mr. Mitchell here. In this video we're going to go over 3 worked examples to show you how to do problems involving nuclear fusion. Now if you haven't already done so, check out my previous theory videos covering nuclear fusion and nuclear fusion reactors, as watching these videos will help you understand what we do in this one. So let's get going. Question 1 says, despite there being no nuclear fusion reactors in use today, nuclear fusion is currently an exciting area of research, and it is thought that it will finally be implemented in the next few decades. Part A says, describe what is meant by a nuclear fusion reaction. Well, remember from the theory video on nuclear fusion, we saw that this is the process of small nuclei joining together to form a larger nucleus with the energy being released. Part B says, what special conditions are required for nuclear fusion? Well, remember we need 2 things. We need a high temperature and a high pressure in order for plasma to exist inside the reactor. And lastly, part C says, how can plasma be contained in the reactor? Well, remember this is by using strong magnetic fields, powerful magnets, and that's to keep the plasma where it is, i.e. contain it, and stop it from touching any parts of the reactor, as if it does, the plasma is going to cool down and the reaction will stop, and also it will melt any parts of the reactor as well. Question 2 says the following statement describes a fusion reaction. So we have hydrogen plus hydrogen going to helium-3 plus a neutron plus energy. It then says the total mass of the particles before the reaction is 6.684 times 10 to the minus 27 kilograms. And the total mass of the particles after the reaction is 6.680 times 10 to the minus 27 kilograms. Calculate the energy released in the reaction. Well, remember to do this kind of question, we're going to use the equation for Einstein's mass energy equivalence, E equals mc squared, but in order to find the lost mass, we need to use the total mass before and after the reaction, which are actually given to us. So that's doing a bit of work for us. So first we want to determine the mass lost in the reaction. So we can say the mass lost is equal to 6.684 times 10 to the minus 27 minus 6.680 times 10 to the minus 27, i.e. we're just doing the total mass before the reaction minus the total mass after the reaction. And putting that into your calculator should give you an answer of 4 times 10 to the minus 30 kilograms. And now we can calculate the energy released in the reaction. So writing down what we know from the question, we're trying to find the energy E. The lost mass is 4 times 10 to the minus 30 kilograms, and the speed of light c is 3 times 10 to the 8 meters per second. Writing down the equation, we have E equals mc squared. Substituting in the numbers gives us 4 times 10 to the minus 30 times 3 times 10 to the 8 squared, and putting that into your calculator should give you an answer of 3.6 times 10 to the minus 13 joules. Lastly, question 3 says the sun is the source of most of the energy on Earth. This energy is produced by nuclear reactions which take place in the interior of the sun. One such reaction can be described by the following statement. So we have hydrogen 3 plus hydrogen 2 going to helium 4 plus a neutron. It then says the masses of the particles involved in this reaction are shown in the table. So we have the hydrogen 3 is 5.005 times 10 to the minus 27 kilograms. The hydrogen 2 is 3.342 times 10 to the minus 27 kilograms. Helium 4 has a mass of 6.642 times 10 to the minus 27 kilograms. And lastly, the neutron has a mass of 1.675 times 10 to the minus 27 kilograms. Part A says name this type of nuclear reaction. Well, if we look back at the reaction, notice how we've got hydrogen plus hydrogen fusing to form helium. So this means we've got a nuclear fusion reaction taking place. And part B says calculate the energy released in this reaction. Well, first we want to find the total mass before and after the reaction. So looking back at the reaction here, we want the mass of the hydrogen 3 plus the mass of the hydrogen 2. And then for the total mass after the reaction, we want the mass of the helium 4 plus the mass of the neutron. So for total mass before, we have 5.005 times 10 to the minus 27 plus 3.342 times 10 to the minus 27. And if you put that into your calculator, you should get an answer of 8.347 times 10 to the minus 27 kilograms. Then for the total mass after, we have 6.642 times 10 to the minus 27 plus 1.675 times 10 to the minus 27, and again putting that into your calculator this time should give you an answer of 8.317 times 10 to the minus 27 kilograms. Now that we have the total mass before and total mass after, we can now find the mass lost in the reaction. So we have that the mass lost is equal to the total mass before minus the total mass after, so we have 8.347 times 10 to the minus 27 minus 8.317 times 10 to the minus 27, and putting that into your calculator should give you an answer of 3 times 10 to the minus 29 kilograms. Lastly, we want to calculate the energy released in the reaction. So we're trying to find the energy E. We note the lost mass m is 3 times 10 to the minus 29 kilograms, and the speed of light c is 3 times 10 to the 8 meters per second. Writing down our equation, we have E equals mc squared. Substituting in the numbers gives 3 times 10 to the minus 29 times 3 times 10 to the 8 squared, and putting that into your calculator, not forgetting to square the speed, should give you an answer of 2.7 times 10 to the minus 12 joules. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.